Ankit. Thank you very much for joining us. So as I said, it's really a pity that we cannot invite you here in person to give you some nice food and coffee to enjoy. But thank you very much still agreeing to joining us online. And we really hope that when the situation becomes better, we can invite you again to campus and to talk to our colleagues here in person whenever the situation allows. So thank you very much for joining us. I think it's not the most convenient, time because of the time zone difference, and thank you for accommodate that. So I would just like to spare a few minutes to give a very brief introduction of Ankit. Professor Ankit Agrawal is a research professor in the Department of Electrical and Computer Engineering at Northwestern University in the US. And Ankit's research is in interdisciplinary artificial intelligence and big data analytics through high-performance data mining, computation, and with a special focus on the materials, but also other areas such as the healthcare, social media, bioinformatics. So really cover a variety range of topics, and he has co-authored more than 150 peer-reviewed publications and have developed and released 15 plus software, so which is again really impressive. And of course, he has won a lot of funding from different funding agencies. So I don't think I need to read all of them, but really impressive. So Ankit, so we are really very much looking forward to your talk about the artificial intelligence and high performance data mining for accelerating scientific discovery, which fits very well with today's topic. So without further ado, I will hand over to you, Ankit, and thank you very much.
Thank you so much, everyone. And this is a great honor to have this invitation, and unfortunately cannot be there in person, but really look forward to this, and maybe future opportunities to be there in person. So thanks very much again for the invitation. So let me see if I can share my screen first. All right. Do you guys see this?
Yes. Thank you very much. We can see. Perfect.
So let's begin. All right. So thanks once again. So today I'll be talking about artificial intelligence and high performance data mining for accelerating scientific discovery. And Professor Yuan already introduced me. So I'm a research professor at Northwestern here in the US. And these are my team members and the different collaborators, because most of the work that I'll be presenting today is AI application in materials. So coming from a computer science background, we work very closely with a lot of domain experts. So here you see different universities and national labs and companies and so on. And these are all the funding agencies that have supported my work. So just a big thank you to them. So let's begin. All right. So a bit more background about the work I do and our group as a whole. So in this era of big data, I strongly believe that within computer science, there are these two fundamental technologies, high performance computing and data mining, AI, machine learning, which need to come together more than ever before if we have to solve the big data challenges. So we call it AI and high performance data mining, as you probably also saw in my talk title. And then personally, I'm also very interested in applying these techniques in different domains like materials, healthcare, social media, and so on. And of course, today it will be mostly materials applications. But that's what the focus of our group is. So being a computer science AI group, we develop new techniques, scale them up, and then work with the domain collaborators to apply them to real world problems. So this is going to be the overview of this talk. I'll start with some basic introduction and some terminology. artificial intelligence, machine learning, data, deep learning, data mining. So there are too many buzzwords, keywords floating around. So we'll just try to clear it up a bit. And then most of the time I expect to spend on illustrative examples of application of that in our group. So both from the HPC side, high performance data mining, how can we scale up these AI algorithms, and then also how to apply them in the context of material science, both for big data and small data. And then in the end, if there is time, I'll try to give a brief demo of the tools. All right. So this is one of my pet slides. If you've seen my talks before, I think you may have seen this already. But this is quite fascinating to me. The way science and technology has evolved over centuries, not just years or decades. We can very clearly identify these 4 paradigms of science. So we started with all science was purely empirical in the beginning. Everything was based on observations. You look in the sky, you look at stars, or you look at different stones, materials around you. So today that is famous as the experimental branch of science, where you actually do the experiments in the lab. Then in the 17th century, when calculus was invented, we could take real world phenomena and formulate them as mathematical equations or laws. So things like laws of thermodynamics or Newton's laws of motion are good examples of that. Then when computers arrived in the 50s, we could now solve these equations on computers and then supercomputers. So the third paradigm of computational science or simulations came into being, and things like density functional theory, molecular dynamics, finite element simulations are excellent examples of that. Over the last 20, 30 years now, the sheer volume, velocity, variety of the data that is generated from these first 3 paradigms has far outstripped our capacity to make sense of it. So even as computer scientists, we have become increasingly efficient and adept in generating more data and storing more data and retrieving more data. But when it comes to analyzing that data and extracting meaningful insights, our capacity has been rather limited. So that's where this 4th paradigm of data-driven science, or AI, machine learning, all that comes into being, where the data itself, the historical data itself is a resource, in addition to all the computation we have, all the physics we have, everything. So that's really at the crux of AI and machine learning. And I described this many years ago now, almost 6 years ago, in this perspective article. Very simple to, easy to read, high-level introduction. So if you're interested, please take a look. So this problem of big data analytics and so on, it's very much like finding needle in a haystack. And I like this example a lot because not only it signifies the difficulty in finding the needle. Of course, the needle is somewhere hidden, and the hay is too much, so it's not easy. But the bigger risk or bigger difficulty is to easily find the wrong needle, because if you're not careful, these algorithms, AI, machine learning, these are very attractive, very, very hot right now. So you can just take an online course or think that without a thorough understanding, you can think that you know now and you can apply them now, which is actually one of the biggest risks that the science and engineering community is facing right now. So if we don't exactly know from either side, either from the AI side or from the domain side, if we don't know the exact limitations and of the AI techniques, or the strengths and limitations of the data, and we just put them together, these techniques are domain agnostic. They don't know whether it's materials data or healthcare data, or where it came from, who collected it, what were the assumptions and all that. So it will give out some numbers when you run the algorithm. And if you're not careful, we can easily fall in the trap of wrong needles. So that's very important to note, and I'll come back to that. So what is AI? Just a brief introduction on these different terminologies. So AI is nothing but the ability of machines to perform tasks that normally require human intelligence. So I'm sure you have seen these kind of charts where deep learning is a subset of machine learning, and that's a subset of AI. So AI is pretty broad. It includes all kinds of other things like expert systems, robotics, and so on. So anything that falls in this definition is basically AI. And this is one of an interesting classification of AI algorithms: weak, strong, and super. So everything that we have right now is falling in the category of weak AI. So even the state-of-the-art example of self-driving cars is an example of weak AI, because it means we can make an AI model which can do very well, even better than humans sometimes, in one particular task, but not everything. Strong AI is when it can do everything a human does, and super AI is all the sci-fi movies where the AI takes over the world. So that's not happening anytime soon, fortunately. And then machine learning, as the name suggests, is focused on learning, which gives the computers the ability to learn without being programmed. So without giving the rules and explicit programming, just by examples of inputs and outputs, it can learn the relationships. And these algorithms, their performance improves as they're exposed to more data, which makes sense. And as you can see, these concepts have been there for a long, long time, but they have always been hungry for big data and big compute. And that's where big deep learning comes in, which is a rediscovery of neural networks fueled by the availability of big data and big compute. So we had neural networks for many, many years, as I said, 50s, and then again in the 80s, it became popular. But we did not have big data and big compute until recently. So that's why in the last 10, 15 years, deep learning has taken off the way it has. And I'm sure I don't need to go into the success stories, all kinds of groundbreaking advances in self-driving cars, in natural language processing, game playing, and so on. But like any other technique, deep learning has its share of challenges and advantages. So we already saw that it requires big data and big compute. Architecture search, neural architecture search is an open problem. There are a lot of advances being made, but often you don't know ahead of time what the best architecture of a neural network would be for a given problem. And then interpretability is another open problem, because although there are many ways you can open that black box and see what the model is learning, but it's very much in its infancy, in the sense that, especially in engineering applications like material science, you want to make sure that the model is learning from the correct features, not just giving good accuracy on a particular data set. Because if you want to scale it up and apply to unseen data in the future, then you want to make sure that it is correct, not just by chance. So that's very important in engineering. So those are the challenges, but the advantages of deep learning typically outweigh the challenges. And the biggest advantage of deep learning is that it's feature engineering free. So you don't need raw, you can actually now work on raw inputs. So just like in images, you can work on raw pixels. You don't need to have handcrafted attributes the way we used to do in the past. And it's more accurate. As you can see, the performance of these algorithms don't saturate that quickly, even though on small data, it may not be so accurate. But most learning algorithms saturate after this point, which is the cutoff. And this point can be different. And we'll see in some of our applications that we have been able to find this point. And these are faster. So although it requires big compute to train the model, the running or the testing of the model is very fast. So you can make predictions in a matter of milliseconds, microseconds, and you can easily parallelize it and so on. And deep learning comes in different size, shapes, colors, depending on what you want to do with it. So the fully connected network is the most commonly used, and the traditional network, where you have input layer, output layer, and a bunch of fully connected layers. So you see each layer is connected to all the neurons in the previous layer and all neurons in the next layer. So these are neurons and these are edges, and they have weights, and that's where the learning happens. The learning of the weights is what the training means. For image data, we can have convolution neural networks. For anything time series like weather prediction or natural language processing and all. Sequence data, we can have recurrent neural networks and its variants, LSTMs, and transformers, and more generalized graph neural networks. And then these GANs, generative adversarial networks, are very interesting class of AI algorithms, where there are two neural networks, not one, generator and discriminator, and they kind of compete with each other. So you can think of generator as a group of criminals who are trying to produce fake currency, and discriminator kind of the cops or the police who are trying to distinguish whether a currency note is real or fake. So as they are trained together at the right rate, which is very important, because then they can make each other stronger and stronger. And at the theoretical Nash equilibrium, they the generator can do amazing things which the discriminator cannot distinguish. So all this deep fake videos and images and all, that's the technique behind it, and we'll see how we have used that gainfully for material science applications. So we talked about AI, machine learning, deep learning. What is data mining then? So data mining is focused on data and extracting knowledge out of data to discover hidden patterns and actionable insights. And they are very related, as you can see that it utilizes methods at the intersection of AI, machine learning, deep learning, algorithms, databases, statistics, and so on. So that's it's basically application of all these techniques on real world data or synthetic data to extract insights. And then high performance computing is nothing but the use of parallel processing to run your programs more efficiently, reliably, and quickly. It's also known as supercomputing. Basically, you distribute your workload over multiple computers or multiple processors so that you get higher throughput. And again, it utilizes technologies at the intersection of algorithms, computer architecture, networking, system software, storage, and so on. So these are just some of the terminologies. I'm sure most of you would be well aware with all this. So in our lab, what we do is we use high performance computing to drive data mining and AI algorithms, which in turn drives big data analytics and knowledge discovery on big data. So that's why AI and high performance computing together can accelerate scientific discovery. So with that, brief terminology overview, let's look at some examples. So one example I want to show first for high performance data mining is scalable deep learning. So there are a lot of examples that we have here, scalable clustering and deep learning and association rule mining. But because deep learning is quite popular, I just wanted to show this one. So as we know, CNNs or convolutional neural networks are very popular for image data, and training of these networks is extremely compute intensive. It takes a long time, from days to weeks to even months if your network is very deep and your data is very big. So parallelizing or using HPC techniques to accelerate the throughput becomes very important. And that there are a lot of different methods like synchronous SGD, stochastic gradient descent. So the way these networks are trained is using stochastic gradient descent. And synchronous SGD basically means that you take your training data and you divide it into mini batches, and then each mini batch is divided into multiple, is distributed across the nodes, and each node works on its in parallel, and then aggregates the results using inter-process communication. So this communication is actually the bottleneck, because this is extra time or overhead that we are wasting to aggregate the results and get the final result. So it doesn't scale very well. That's why. And local SGD is another way to do this parallelization, where different, let's say there are two workers or two processors, they apply this SGD in parallel separately, and periodically they communicate. So they don't communicate after every iteration, but only periodically. So that reduces the communication time, but still it has a overhead, and it doesn't scale very well. So large batch size and large number of workers can improve scalability, but degrades accuracy. So as you see here, if you increase the batch size to 256, which is this green curve, this is accuracy versus epochs. So higher the better. So for large batch size, you can get a good speed up, good scalability, but not a good accuracy. And like that, there are many different challenges. So over the years, our group has used different ideas like communication efficient, gradient averaging, overlapping the computation and communications, adaptive mini batch size refinement, adjustment, and using both the synchronous and local SGD in a hierarchical fashion with optimal workers to speed this up. And there are a lot of details here which are in these papers described, but I just want to show a couple of results here that using these methods on a particular data set, div2 data set, using an EDSR model, which is a super resolution image super resolution model, we could get about 81 times faster training, or 81 speed up on 128 nodes, which you see here, this point, which means that the training which takes more than 4 days could be done in less than 1.5 hours. And another data set, CIFAR 10, I'm sure many of you may be familiar with this. using this ResNet 20 model, you got a speed up of 32 times on 128 nodes, as you can see in this figure, where all the other methods fail. In fact, they give less speed up after a certain number of processors. So it's very, very challenging to parallelize these training algorithms. But using these techniques, we could get 32x speed up, which reduces the training time from over a day to less than an hour. So as I said, a lot of details in these publications, and there are more examples of parallel clustering and parallel association rule mining that our group has developed. And there's another research faculty in our group who leads this line of effort. So if you're interested, I'll be happy to talk more and connect you. So that's just one example of how we can use HPC for scaling deep learning training to tackle the big data problem. Now let's go to some examples in the materials domain, and we'll look at both big data and small data challenge. So before that, I just want to spend a couple of minutes in having an overview, because I'm coming from a computer science background, and if there is one thing I've learned from all the domain collaborations with material scientists over the last 10 years, is that everything in material science depends on these PSPP relationships: processing, structure, property, performance, where the science goes from left to right and engineering goes from right to left. So processing is the cause, structure is the effect, structure is the cause, processing is the effect, and so on. And if your goal is to get high performance or a target property, then the means to achieve that is to work on the structure, work on the processing, composition, and so on. And interestingly, these are many to one relationships. So a lot of different processing routes can give the same structure, and the same property can be achieved by multiple structures. So what that means is that the forward problem of prediction is easier, because given a material, there's only one property. But the inverse problem is harder, because for a given property, there can be many materials, and ideally you would want to know all of them, so that you can choose which is the best, maybe some other property with respect to other properties, or with respect to cost, manufacturability, and so on. So AI, or materials informatics in this space, can generate these fast forward models for predictive analytics, where you can express property as a function of a representation, where representation can be either processing, composition, or structure, or a combination. And then these forward models are very fast always, because these are AI based models. They don't need to solve differential equations and like simulations and so on. So they're always fast, but if they're also accurate, which again depends on how closely your computer scientists and domain scientists have collaborated to understand each other's language and challenges and so on. So if they're also accurate, they can help in the inverse models of optimization and design, because these AI models can serve as a very fast and accurate proxy for simulations and even experiments, so that you can scan your search space of possible materials very fast. So again, the same article, I go over this if you're interested. And then over the last 8 to 10 years now, since MGI was announced, actually 10 years now, because 2011 is when MGI was announced. So that's when we became interested in this AI for materials. So over these 10 years, we have had a lot of different works for both forward models of property prediction, inverse models of discovery and optimization, and structure characterization. This is a slightly different problem, although technically it's an inverse problem, but it uses methods from the forward model. So I list it separately because it uses image data. And here I show the both CS or AI publications in red and domain publications in green. So we try to reach out to both the communities to spread these advances and for the community to build upon. Also, a lot of software and software tools available here, and a lot of code available on our GitHub website, which I'll talk about at the end again. So now let's look at some examples. So first, I want to give some examples of how to tackle the big data challenge in material science. Although that's not often the case, more often we have the challenge of small data, but sometimes with simulations we can have hundreds of thousands of data points. So that is pretty big for material science right now. Of course, it is nothing in other applications like astrophysics and all, where we can have billions of data points. But for material science, I think 100K plus is quite big. So in this example, we developed ElemNet, which learned the chemistry of materials from scratch. So as probably you guys are expert in this, I don't need to give introduction of what DFT is, but you all know that this is very slow simulations and it requires crystal structure as an input. So we use data from OKMD, which is at Northwestern, hosted by Chris Wolverton's group, and from NIST Jarvis dataset, and use that for training these models. And we have a bunch of models, composition-based models, where you can either use just the raw element fraction, or you can use these library of attributes. So for example, for ferric oxide, Fe2O3, you can calculate these bunch of attributes like average atomic mass, average electronegativity, and so on. And all these numbers, the vector of this can serve as a numerical representation, a composition-based representation to train the AI models. And then similarly, we can also have structure-aware models, where we can look at the environment of each atom and quantify that, like, average bond lengths and so on, and use that vector as the representation. So you can have composition-based representation or structure-based or both. So that's very much desirable, and we should always do that whenever we can. But as computer scientists, we were also very interested in a diametrically opposite question, that what if we do not provide any domain knowledge to the model? What if we do not provide any composition structure model, structure information? We only give raw element fractions, because that's where deep learning excels, right? Because in all these self-driving cars and all the computer vision algorithms, they just look at the raw pixels, the raw image. There's no processing ahead of time. So we thought, what can we do if we only give raw element fractions? So when we did that, we found that if we have the right data, we can actually end up with 20% more accurate and faster models, and it can also learn the chemistry of materials. So here you see this top curve or blue curve is random forest, which is a traditional machine learning algorithm, and it is trained on elemental fractions only. Just the fact that it, so for example, for ferric oxide, just the fact that it has 40% iron and 60% oxygen, nothing else, no atomic numbers, nothing. And this green line is the same random forest with physical attributes. So when you give all these attributes, so in a way you are supplying domain knowledge, periodic table information, valency information, then it reduces. So this is error, and this is the training data set size. So this green curve is much lower than this blue curve. But then we found if you use this ElemNet model, which uses only element fractions, so the same input as this, but for very small data, of course, it's not good, but it very quickly beats the blue curve with a couple of hundred data points, and the green curve with a few thousand data points. So this is the cutoff point for this data set, that just with if you have a few thousand data points, you can use this ElemNet model and you can have significantly better accuracy. I don't know if you can see here, but all these have error bars, but the error bars are very, very small cross validation. So this is a significant difference. And then we also found that it learns the chemistry of materials in some sense, because we found that the model somehow knew that sodium, potassium, cesium, lithium, these all are somehow belonging together. Although we did not give any valency, atomic number, nothing. But just the model, when we try to do some interpretation of the model using activation analysis and so on, we found that it is treating those elements together. And it also knew that group 1 and group 7 in a 1-to-1 ratio will give a stable compound, and group 1 and group 6 in 1-to-1 ratio will not. So it was quite fascinating that the model could just self-learn this chemistry by itself. And then we also did some stringent tests where we held out some systems, like in this case, titanium oxygen system, and the model was able to recover the convex hull quite well. So this orange curve is the convex hull by ElemNet, and this black is the ground truth from the DFT database. And random forest, which is this green curve, using physical attributes, was all over the place. So that really gave us a lot of confidence that this model is actually learning something. And then we did combinatorial screening of more than 500 million quaternary compositions to identify stable compounds. And we also have a tool where you can plug in your compounds and get predictions. So why? One thing I forgot to mention: this ElemNet is a 17-layer model, and we found that beyond that, the accuracy saturates. So, but why not go deeper? Because we know deep learning is very powerful. So why stop at 17? So the issue is that there is something called this vanishing gradient problem. So the way these networks are trained is that the gradient of the error with respect to the weights is backpropagated to update the weights. So when the network is very deep, the gradients almost die out. They become zero, close to zero, because these are very small numbers between 0 and 1. So when the network is too deep, then there is no more training. As you can see here, this is error versus iterations or epochs. And this is a 17-layer curve, the ElemNet that I showed in the previous slide. And then when you make it 24 layers and 48 layers, the error actually increases. The model becomes worse. So building upon the ResNet idea, the residual learning, which was originally used for images, one of our students introduced this individual residual learning, where he added these skip connections after every fully connected layer, so that the gradients can move more freely and backpropagate nicely. And then recently, and a couple of years ago, we got this KDD publication from this based on this work. And some of you may know that the KDD is the topmost data mining AI conference in our field. And very recently, we did a thorough evaluation of this model on materials data sets from big data sets, 400,000 plus, to small data sets like experimental 4,000 and so on, with a lot of different properties, 10 different properties, as you see here, and 4 different material representations: composition, structure, composition plus structure, and composition, structure, and elemental fractions all combined. In total, we had almost more than 30 different data set, property, and representation combinations, and that allowed us to do a thorough evaluation of how this model is behaving. So here you see on y-axis the relative MAE, so which is the MAE of IRNet divided by the MAE of the best machine learning model, which was identified by thorough grid search with over 10 machine learning algorithms. So basically, the best machine learning algorithm is on this x-axis. So anything below that is a lower MAE, so better model. So we can easily see this trend here, that for very small data sets, machine learning is better than this IRNet model or deep learning. But around this point, which is around 20,000 samples, we can take advantage of this deeper learning idea and make models with up to 48 or even bigger or deeper layers, and get up to 40-50% improvement in our model error. So this IRNet was always better than PlaneNet, and better than best ML when we had more data points. So this is kind of the threshold in general for this work. And the more details in this scientific reports article from last year. Another example from finite element modeling domain. So again, I'm sure you know finite element simulations are very powerful for doing this homogenization and localization models. So here the problem is that if you have a two-phase composite, and if you apply force or apply a loading condition on top of it, how does that get distributed at the micro scale? That is in a sense the localization problem. So it's very challenging, because from just two-phase or 0-1, we need to go to real numbers. And we used we tried a lot of different models for this problem, and we found that a special way to apply 2D CNNs or extending it to 3D CNNs, they work quite well. And I'll not go to too many details here. They are there in this article, but just to give some results on 2 different contrasts data sets. So contrast basically is the ratio of the Young's modulus of the black and the white face. And you can imagine higher contrast means more difficult data set to predict. And we were told from our collaborators, this is worked with collaboration with Surya Kalidindi's group at Georgia Tech. So we were told that these are very high contrast values. So most of the existing models can barely work with contrast 2 or contrast 5. So 10 and 50, they are really very high, and most of the existing models that they have would fail. So we find here that this is the finite element result, 2 example slices. And this is what we got from deep learning, and this is from their benchmark or baseline model MKS, and you can see that these hotspots are well predicted using the DL method, but they are missed here. Similarly, in for contrast 50, the deep learning result is quite close to the ground truth, whereas this MKS model gives a lot of spurious hotspots. So these hotspots apparently are more very critical to identify where crack initiation is expected to happen. So it is critical to predict them correctly. So again, more details in this ActaMat article. So those were some examples of big data sets and how we can take advantage of deep learning on big data sets. So all these data sets were 100,000 plus. But as I said, most of the time we have small data problem in material science. So what can we do? So there is this idea of deep transfer learning that we have applied over the years for small, especially experimental data sets. So as we know, most data sets are small, and we are using DFT to train the models till now, right? The OQMD and Jarvis and all. And DFT is not ground truth. So there is some error with respect to experiment, which is about 0.08 electron volts per atom in the data sets that we analyzed in this work. So what if we want to build models for experimental data directly? So we can either do it from scratch, like you see here. This is the x-axis is the training size. So if you build the model from scratch, this is the error you'll get. And as you have more and more training data, the error will reduce. But we can also use the simple and elegant idea of transfer learning, where you first train here we first train an ElemNet model on OQMD, which is a DFT data set, which is big, and we use that resulting ElemNet model as a starting point for the target training. So you have a large source data set, do model training, get a source model, and then for the small target data set, this source model can be reused in different ways to get the target models. So one way is to do fine tuning, that you just use that ElemNet as a starting point, and then just instead of random weights initialization, you use the trained ElemNet model as the initial model and then do the learning. Or you can do feature extraction. So here you see this is the fine tuning method and or feature extraction. So from different layers of ElemNet, you can extract the activations and use them as the features for your target data set. So we applied that a couple of years ago. We got this Nature Communication article in 2019 for the same property, that if we have the same formation energy as the source property and the target property, then we can do that. But recently we looked at what if the target property is different, because for formation energy, fortunately, we have big data set. But for some of these properties, we don't have big data sets available, even in DFT, or at least it's not openly available. So what can we do then? So can we do this cross property thing, that we train on one property, but try on different property? So we tried this cross property idea on 39 different properties from the Jarvis data sets, which were ranging, and these data sets were ranging from like 500 data points to 20,000 data points. And OKMD, of course, is more than 300,000 data points. So when we did that, we found that these models, the transfer learning model, as you can see, it's already quite accurate. And we can get up to 50% reduction in accuracy. And on the cross property case, out of 39 properties, on 38 properties, the transfer learning model was better. If the scratch model is built only on elemental fractions, so that blue curve that I showed before. But if the scratch model is allowed physical attributes or those library of attributes, then we are making the scratch model more powerful, while the transfer learning models are still using only elemental fractions. So this is a more stringent test, where we are giving some advantage to the scratch model. But even in that case, the transfer learning model was able to beat the scratch models in more than half of the cases. We did some more analysis in terms of extrapolation. So in a separate model training, we only gave this part. So on the right of this blue line, that was given as a training data set, and then it was tested across the whole regime of this formation energy values. So you can see in the interpolation regime, both the scratch and training models are doing reasonably well, although the transfer learning model is slightly better there also. But in the extrapolative regime here, the scratch model just fails, because it has not seen anything like this before. So there's a big error But the transfer learning model, although there is a bigger error compared to the interpolation regime, it's still somehow, somewhat close to the diagonal. So these transfer learning models have much better extrapolative potential, which is a big deal in machine learning, and especially for these applications, materials applications, where the goal is to discover new materials which have not been seen. So you, by definition, need the model to do extrapolation well. So that was example of using transfer learning on small data. Another small data sets in the plasticity regime that we got from our collaborators from NIST and West Virginia University recently, where the problem is to identify plastic deformation history. So again, I'm sure you guys are more familiar than, or expert in this than me, but this is a typical stress strain curve. And when you subject a material to a loading condition, it, let's say, goes to this red point, and then let's say you release that load, so it goes to this blue point. So at this point, the material has some strain, but let's say that's unknown. And the goal is now to take this and see and kind of try to predict whether we can tell what that prior strain was. Because if you buy a material from a shop, from a manufacturing shop, how do you know whether it was this metal has not been in an accident in a car or something? Because just by looking at it, we won't know. So the way they do it is they apply a slight test load on this, so that this material goes to this green point, and then using that they can get these strain maps. And we believe that these strain maps have all the information that we need to identify what the prior deformation was. So we got this data set about 3,000 strain profiles, and this is image data, so it's not a big data compared to all the ImageNet and all that we have. So with different sample weights, so you can see it goes all the way from 2 micrometer down to 62 nanometer. So really at the nanoscale. And three labels: high deformation, medium, and low, and 2 different slips. So there's 1 slip and 2 slip system. So in total, we had around 3,000 strain profiles. And because it's a small data, we first did some data augmentation, very carefully designed 24 crops, so that this data could be expanded 24 times. So we had 87,000 data points now. And there is some detail here that, how you train and test this model, because if you just take this as your training data and just randomly split it into training and testing, you will most likely end up overfitting the model. So there is some detail here which we can talk later if there is interest. But then we use this residual learning idea, and we found that the baseline model can give 68% accuracy, which is actually quite good, because for a 3-class problem, the random model or the base model or random guessing will only give you 33% accuracy. But this model, the base model was already, correlation-based model was already 68% accurate. But when we applied this, our proposed model, we could get 92%, and if we combine the top performing models, it could reach almost 94%. And this was very fascinating to our collaborators. And another great thing about this model was that it could predict stress strain curves. So here you see the red is the actual stress strain curve, and then blue is the predicted. So as you decrease the width of the sample, it becomes harder. But this was quite encouraging for us, and the collaborators were very happy with this. Again, more details in this scientific reports article. This is an example of GANs, the generative adversarial network that I talked before for microstructure design. So again, I'll not go to details. I think I'm running a little bit behind time now. So here the challenge was to identify a low dimensional representation of microstructures. As you can see, this microstructure is an image, very high dimensional. So using this generative adversarial networks, generated and discriminator idea, after proper training, we could have a generator which could generate these artificial images. So these are on the first row, you see the original images, and these are the generated images, and they are all very, very similar. Not just visually, but also in terms of statistical correlation and linear path correlation, 2-point correlation, all kinds of tests we did to see that these are really statistically similar. And then when we combine that with the Bayesian optimization loop, we could use it for inverse design. So once we have an ability to generate a microstructure, we can now optimize the property. And here you can see in just about 100 iterations, we could get to this optimal property, which in this case was optical absorption, and 70% better properties than what have been observed before using other optimization methods. And there were some other side properties which were beneficial, like scalability of the generator. So the same generator could be used to generate different resolution images, which previous works could not do because of fully connected layers. But we start with a noise vector here, which is just 4 by 4, 16 random values. But if we just increase this to, let's say, 5 by 5 or 3 by 3, or we change it accordingly, we can use the same network to have different resolution of images, and all of them are statistically similar. So just a quick example of what GANs can do in this domain. And of course, we have some follow-up work, which is right now under review, which speeds up this optimization loop. I think this is my last example, industrial materials design. So lately, or the last few years now, there has been a lot of interest from industry. A lot of companies have approached us to try to understand and learn these AI techniques and integrate them in their workflow. So this is one example from a relationship with Toyota that we have. So here we got some data from them, and of course there's a lot of things that we cannot share because of NDAs, but this is part of the work that was published. So as we know, this a typical industrial processing workflow may look like this. So in this case, it's for magnets. So you start with the samples, and then you have it go through rapid cooling, molding, hot deformation, and so on. And you can calculate the property at different points of this workflow. And since it is experimental, industrial, and very small, there are a lot of challenges because it's quite small, just a few hundred points. It's very, very costly to do these at scale, and it's also heterogeneous because you can have composition data, which is numerical. You can have image data, structural data, which is images, and you can have X-ray diffraction data, which can be image or a 1D vector or a signal spectrum, and so on. So that's quite challenging, and it's noisy because it's experimental. It doesn't have the set patterns that we expect in the simulation data sets. So to counter all these challenges, one of our students, he developed this combination numerical plus image model workflow, where using the transfer learning, the same idea, the transfer learning idea, where we, in this case for images, where we start with these structure SEM images, and then using pre-trained ElemNet models, pre-trained VGG models on ImageNet, we can extract the features, the same feature extraction idea. And then using PCA, we can reduce the dimension and add the composition information, and then train a machine learning model of choice, in this case, gradient boosting. So, of course, there's a lot of back and forth with the collaborators, like it always has to be. But once we did all that, we ended up with a model which had less than 5% prediction error for the coercivity and remanence. These are the two important properties for magnets. And more than that, once we had this accurate model, it was a game changer for them, because now they can use this model for prioritizing what experiments to do. Only perform relevant experiments and avoid higher end processing, because if you know that some material is not going to perform well ahead in this workflow, then you can save higher end processing, reduce the SEM man hours, the equipment time, the person time. All this results in huge cost savings. And then, of course, all that can translate into, because now you are saving time and money and resources, so you can use them in the right direction and identify the most promising processing routes for faster magnets design. So again, some publications that describe this in more detail. All right, so some of this, or most of these works that I described today, and a lot more, both from our group and others, are discussed in this prospective article, AI Perspective in MRS Communications, a few years ago. So you can please take a look if you're interested. So I don't know how much time I have now. What's the time? Is there time for a quick demo? Jin, or?
Yes, maybe if you can have a quick wrap up or showcase the
Okay, wonderful.
few last slides, that would be great.
Yeah, sure. So you can go to this website. Do you see still the presentation or the website now?
I think we still see the presentation. I mean, starting with the software tools.
I see. Okay, maybe I have to.
Yes, now we start to see. No, it disappeared again.
Oops. Okay, how about now?
Yes, yes. Great.
Okay. So on this website, here you see all the tools that we have developed. And again, just to remind, we are not a material science group. So a lot of tools for AI and HPC and material science, healthcare, social media. So let's just look at some material science for now. So this is a steel fatigue strength predictor where you can put the steel of your choice. This is a very small data set from NIMS, Japan. But it's actually quite big considering that it is experimental, and NIMS took almost 40-50 years to get this because it's very costly. So here you can put the steel of your choice, composition and processing, and then in real time it can predict the fatigue strength of this steel along with the uncertainty. So I didn't get a chance to talk much about this, but uncertainty is very important in these predictions, in anything, but especially for engineering applications. So I just want to give a quick demo of why this is important. So this particular steel is predicted to have this strength and this uncertainty. So just let's remember it, 500 plus minus 50. So now let's see, let's say if I make the carbon content ridiculously large. So this model was only trained on this range, but if I make it 10%, so the model knows that adding carbon helps, right? Because carbonization makes it stronger. So let's see what happens. So from 500 plus minus 50, it blows up to 2000 plus, but at the same time, the uncertainty blows up. So that tells me that this is not a useful prediction, and you should not probably use this steel and go in the lab and make it. So that is very important, as I said, for these kind of applications in material science. So we do that for all our predictions, and it is there are different ways to do that. Similarly, we have this formation energy predictor, which predicts the formation energy. You can just put any composition of your choice. It doesn't require any structure. And there are different models, but the ElemNet model is the most accurate, right? In fact, we have some newer models that we are in the process of updating this, but it has the deep learning models already. And then same for thermoelectric toolkit, thermoelectric properties like Seebeck coefficient and so on, and Martin-Side start temperature and organic photovoltaic predictor and so on. So there are a lot of tools, and also for other domains if you're interested, healthcare and so on. So let me just conclude here. So of course, there's a lot of code also, not just tools. You can go to our GitHub page and download code and build on it and so on. So this is my last, ending slide. So I just want to end with this. There's some, so being a computer scientist and interacting with a lot of domain collaborators over the years in materials and healthcare and climate science and so on, I typically find that there are typically two kinds of people I've seen. Either some people think that AI and machine learning is magic; they will just solve everything overnight. Or some people think that it is just a hoax. It cannot do anything because it doesn't have physics knowledge and so on. So that's not the case here, because some people think that it is too easy, or some people think it's just not worth it. So if big data analytics and AIML is not like just drinking from fire hose, because and this goes back to my false needles example, because if we are not careful, we can easily end up with something like this. And there are numerous examples of AI gone wrong. If you see, because these techniques are so very easy to misapply. As I said, you can just take a course and think yourself as a data scientist, but unless you really spend the time and effort, just like any other science, like I have to spend time and energy to learn DFT, for example. Otherwise, I cannot claim myself to be a DFT expert. So similar, but somehow it has, because these techniques are very hot and apparently very easy to learn, there is a big risk. In fact, I was attending a talk recently from someone at Google, and I like the way he put it, that AI and machine learning gives opportunity for great science, but at the same time, it gives an opportunity for terrible science, because there are again, same thing. It is so easy to think that you know it, and then just take some data, take some technique, apply, and then you're nowhere. So it's very important to have these kind of mutual collaborations between the science domains and the AI domains, where we can feed each other and help to generate the right data and generate the right models and so on. So I think with that, I'll stop. Thank you so much for your attention and the invitation again. I'll be happy to take any questions.